Welcome to part 3 of the study case, where we are discussing the single-phase inverter, an example from a textbook. So in this tutorial, we are supposed to show you how to calculate the harmonic spectrum of the voltage and current of the inverter output, and then plot them relative to the varying modulation index. To do that, let's take another MATLAB script. So VA versus V1. Sorry, MA versus V1. MA represents the modulation index. V1 is the fundamental component of the voltage output. So I'll start writing the script, so to speak, if we also have some other plots to close them. Let's call the data folder, which we need to specify. Remember, we had the data saved under this folder. So let's copy this folder name or directory. Save it here. So in order to regulate the reading of the data, to control them in a logical manner, we will need to copy some parts of the previous code, which is this one. This part. So that we run synchronized with the simulations that we ran before. And to calculate now the Fourier series components, we need some additional variables. Let's take the maximum number of harmonics. So 400. Maximum number of harmonic components. We need the base frequency, which is 60 Hertz, and the corresponding time period would be 1 by FP. Now we need to call a function that calculates the Fourier coefficients, and for that we need to specify a certain time period or time space between or in which the Fourier analysis has to be carried out. To do that, we need to specify a start time. Let's call t start. I'll call it 20 milliseconds. Now this has to be in a steady state operation. You will have to figure out from the simulation results when the results are already stabilized, and then specify a particular range of time there. And t end, I'll call it, that should be a period. That means t start plus t. That means one period. This Fourier series is a period signal-based analysis. I will take a helping variable, which is half the period. That means t by 2 for calculation of the Fourier coefficients, an and bn. And since we need only the fundamental component at this point, I take a variable called v1 array, that means array of the fundamental component of output voltage, and allocate the variable to be 0, and then has to be number of runs. This is the size. Let's now write the main loop for that, for the calculation. So here is also a suggestion, but this is not what we're going to use. Let's take I is equal to from 1 to number of runs. Yes. Remember, we have the file index running from 0. That means we need to take the file index and adjust them, which is I-1. We can take a note since the file names start from 0. So let's defining full file data folder, which we have defined on the top. Let's show vout. So I forgot an apostrophe. Vout underscore %d dot mat. So these are the files that are going to be read, and we need the file index for that. And if this is the case, we can just start reading or start creating the array, which is v1 array. I is equal to, now as I said, I need to define a function to calculate the Fourier series analysis, and for that I just call it vcalc fundamental, and that should take some inputs, the file name to read, hmax that we specified, base frequency, start time, end time, and L. Yep, this is the end. Now it's time to write the function. So let's take, we could also define the function down below there somewhere here, but let's take a separate file for that. I'll call it a function, since it's a MATLAB function, and call it V1 as the fundamental component of the voltage. How did we define our variable there? Not the variable, the function. vcalc fundamental. So we need to take this function vcalc fundamental, add it here, and as I said, it takes the file name as input, hmax, fundamental frequency, the start time, end time, and L. I will then construct a structure, which is data struct, and then we hit load the file. File names, in that case, file names underscore is equal to field names, or file names. I apologize. So the field names we need to specify. Data struct, and the data is data struct dot field names underscore 1. So this is the way of reading or extracting the time series data. Now we can take the variables. So field names time, then data dot time, since the time data, time series. load is the voltage, or could be current as well, but for this case it's going to be the voltage. Data dot capital data, read the data. Now let's extract one period. And how to do that? We need to so we specified already one period by this time t start and t end, and we need to find the index or indices of these two times, which we can do easily by time greater than t start. This is one condition, and it's a bitwise operation, so t less than or equal to t end. So this should give us the index. So t range, that means we also need to read the time for that particular period. So t range is equal to t of idx. U range is equal to, from that variable, which is the load voltage, idx. Now it's time to compute the Fourier coefficients. An in this case is equal to, so before I write the loop to calculate the an and bn, let's just assign the variables to zeros, or pre-allocate the space for them. It should run from the number or maximum number of harmonic components. Bn should follow a similar pre-allocation. That's all, and now comes the for loop. For I is equal to 1 to h max, since our maximum number is 400, as we said, an n, not an to continue to ani actually. Ani should be, what is the formula? It's 1 by L times, we need to integrate trapezoid drop of, we need to give the time first, t range, and then the variable itself, u range. And then comes for an, we have a cosinus part. So we take component-wise multiplication with cosine of I times t range by L. The same we need to do for B. Perfect, it's already suggesting us to do that. 1 by L, trapezoidal of t range, e range, sine. Perfect, and we can end it. We can also show the harmonic, or the nth order harmonic, as square root of an. It has to be, as this is a vector, so it has to be n squared plus bn squared. Now we can take v1 is equal to hn and one first component. And we need to close the function. So, of course, if we save it, it's going to take the function name automatically. And we're saving here. Perfect. So what we're doing now, just see some literature how to calculate the Fourier coefficients here. I'm using, it's 1 by period, or half of the period, so to speak, then the integration of the signal itself, and then multiplying once with cosinus terms and another with sinusoidal terms. And this ultimately gives us these two coefficients. And then we can calculate the fundamental component, which is the first elements for each calculation. Right? Yep. So here we have calculated for number of runs we have to check. So let's see if we have included everything. So the calculation is there. Once the calculation is done, of course we can, or we have to now show the results as well. So plots, for example. Let's take a figure. It's a bunch of suggestions, but let's do it what I know. So I will take plot, then a values, which are then the spectrum or the series of vector of the modulation index or indices, V1 array. This is right. Let's just run if everything is fine so far. Field name underscore undefined. Okay. Field name. So if we enter this function, so I have written field names, but here it's field name. So I need to include S. Typing mistake. I also say another typing mistake here. Hmax. FP should be there. Save them. So it now calculates it and gives us this expected plot. Very beautiful. So let me suppress the value first. I don't want to see them every time. So let's just suppress this. Rerun. So it takes a little while. So I didn't label the axis yet, but you see this beautiful graph here, which is otherwise very complicated just to plot from hand calculations. So we have a sweep of simulations. So let's see, check some values. I can't wait to check the values first. I will label them later. So X is 1. That means MA is 1. And we have 100% of the value. 100 volts, so to speak. It's the DC, yes. V1, fundamental components is there. V1 array. And then after this point, if you increase the modulation index, you say it's going to saturate. This is what we were expecting actually. So let's rename these values. So I'd like to call them. So is this the only plot that we need? Yeah. Plot these values. Let's add some cosmetics to it. Let's take for this O and this line. Let's increase the line width a little more. Line width. Let's take 2. Next label, modulation index. Modulation index MA. Our label, fundamental component. That's voltage. Grid on. We have an error. Line, yeah, again, typing mistake. It is line width, of course. Yeah, now you can see at each time, or not time step, but MA step, the values here. Output voltage, index, etc. Very nice. What else can we do? One thing we can do again is to check for 0.8 modulation index. So remember where is my solution? Okay. Chapter 8. This is the fundamental component for the voltage was 80, and for that particular case it was a modulation index of 0.8. Now if our calculation is correct, we should see from the plot the same value, otherwise it makes no sense. Okay, so we need to go to 0.8 modulation index. I think it's here. So at 0.8 we have 80 volts, which was exactly the case here, 80 volts here. If you run manually and check for other simulations, like if you have 100% modulation index, it's 100 volts. And 100 volts is exactly our DC link voltage. This is what we should expect. So that means the script, the function is just working fine. And if we go even beyond, we are supposed to see a saturation. 125% here for the maximum 3.5. So it saturates somewhere value. I need to check what is the amplitude of the final saturated value. It should come from the Fourier series analysis, 4 by pi and something. I forgot the formula exactly, but it should saturate to a particular end value here, somewhere here. So let's call it a day today. I will continue my discussion later. And until then, thank you for watching. Stay tuned.